question here, I've set up all the forces, okay, and we're told that the system is in equilibrium, okay. So if the system is in equilibrium, then there's no movement, okay, essentially. So that means then, you know, if we resolve, right, and we focus on B, for instance, so at B, we can literally say that T is equal to 5G, okay. That's an interesting one, because straight away, you know, I focus on B to start with, because we can see straight away that the upward force here, the tension in the string, has got to equal the weight. So we've got a value for T straight away, okay, and it's 5G, all right. And then if we look at A, okay, and at A, you know, if we go sort of along the direction of the string, well, you've got the same tension then in the string, okay, because it's a smooth pulley, all right. Tension is the same throughout. It will equal the friction, won't it? Okay. Right, the tension there will equal the friction. But of course, we know that the tension is 5G, yeah? So that means that the friction has got to equal to 5G, all right? Then, we know, of course, with the equation for friction, okay, friction is mu r, yeah? But actually, the proper equation for it is friction is less than or equal to mu r. It's only equal to mu r when friction is at its max, okay? And it's at its max when the system is in motion, okay? Or when it's on the point of moving, okay? When it's literally cannot do any more work in terms of friction. But the general value for it is always going to be less than or equal to mu r. It doesn't have to equal its maximum possible friction value. It really does depend on what sort of force is opposing it, okay? So because it's in equilibrium, we know that's true, okay? So all you've got to do then is, of course, is put your 5G in here for friction. Now, we've got mu then, and we need to have R, right? Now, remember, R is just the reaction, okay, that the table exerts on the object. And because there's no motion vertically, we can also say, right, that R will equal to 9G, yeah? Okay, when we resolve vertically. So therefore, we can put that in there, and then we can take the 9G over. Okay, and we've basically got the answer. Now the G's will cancel, gravities will cancel, and we can rewrite the mu then with a way round and switch the inequality. And we've got greater than or equal to 5/9, which is what they want, okay? So in part B then, they say that mu is equal to 0.5, okay? And it says show that the magnitude of the acceleration of the body A is 0.35. So if I go back to my picture, back to my diagram rather, we're accelerating now, okay? And we've got to show that it's 0.35. And essentially, all we need to do is just use Newton's second law in the direction of the motion, okay? In terms of along the string. So if I do that using Newton's second law, okay? So in the direction of the string, so in the direction of motion, well, we've got, you know, if we look at A to start with, then we've got, because it's going that way, okay, so it will fall. This weight is gonna pull the cable down, and it'll drag the object A across there, right? The weight of object A, of course, is sort of supported by the table, yes? That doesn't come into play in terms of the motion of it horizontally here. The string's going to pull it, and it's going to move this way. So at A, then, it'll be T, take away the friction, okay? Which will equal to mass times acceleration. So the mass of A is 9. Okay? And then at B, it'll be the weight here, 5G, take away the tension, okay, will equal to 5A. Okay, so we've got equations 1 and 2 there. And what I hope you notice then with 1 and 2 is we can add them. If you add 1 and 2, okay, the tensions cancel, don't they? The T and the minus T disappear. So you end up having 5G minus FR equals to them, those two added together, which is 14A. All right. Now, of course, because it's in motion, okay, FR will equal to mu R, yeah, in this case now, right? It won't be less than or equal to mu R, it will literally be at its max, so it'll equal mu R. So we can then sub in mu R, okay? So remember now, mu, it's stated in the question, is 0.5. The reaction, which we worked out here, is 9G, okay? So, so 9G, 9 times 9.8. and that will equal to then 14A. And then when you work this out here, that should come to, my calculations earlier, comes to 4.9 equals 14A. So therefore A then will be 4.9 divided by 14, which is, as they want, 0.35 meters per second squared. Okay. All you've got to do then to get the tension is sub it in then to one of these equations. Okay. So, you know, maybe sub it into the second one here. So sub into 2. So you have 5G, 5 times 9.8. Take away then the tension equals 5 times A, which is 0.35. Okay. So that comes to, of course, 49. And this comes to 1.75. So if you rearrange that then, I get tension out to be then 47.75 newtons.